Hello all and welcome to my YouTube channel. Today we are going to see an interesting topic. We'll be comparing RAG versus the Agentic RAG. You might be aware about the traditional RAG approach. So RAG is nothing but a retrieval augmented generation, and Agentic RAG is nothing but the RAG operation but is managed with the help of agents, AI agents. Now, you might be familiar with the RAG operation, but in this particular video, we'll be deep diving into the RAG, how exactly the RAG operates, what is the basics behind the RAG, how exactly it operates, and then slowly we'll be moving towards the agentic RAG. So let's get started without wasting the time. So as we all know that RAG is nothing but a retrieval augmented generation, but where exactly it is used and why it is used. So let's understand that part. For example, whenever you are building any AI application, let's say you have a user and this particular user asks one particular query. Now this particular query goes to the large language model. Now in our case, let's say the large language model is, let's say, GPT-4o. This is our large language model. Now whenever user is passing this particular query to this large language model, there is always we pass several instructions, and those instructions we pass as part of our prompt. So we pass this particular prompt first, and through that prompt we are setting several instructions to the large language model, and then whenever this user query comes in, we add that query into this particular prompt and then we pass it to the large language model. Based on this functionality, the large language model is having this particular capability to generate the response, and this response is based on the instructions that we have set. So this is going to be your final output. Now what happen is these large language models are trained on some data set. Now if the query that is asked by the user is not available inside that data frame, then these large language model fails to generate the response. And in order for our large language model to answer our custom questions or to answer on the real-time data, that's where we use a RAG operations, or that's where we use a RAG technique. Now, what exactly RAG is? So RAG meaning we store some data set into this particular vector store. So let's say this is our vector store. Into this, we have stored some of our data. Whenever our user is asking the question, first the query in this case goes to the vector store. From vector store, we are fetching some records. So these records are nothing but, let's say, top k records. K can be any number, top 2, 5, 10, whatever it may be. That response then we are adding into the prompt, and that we are passing to the large language model. Now what exactly this vector store is? This vector store is nothing but our custom information that you have passed. Now this custom information can be anything. It can be your organizational data. It can be your medical field related data. It depends, right, based on the use case. Now in this case, if user is asking any question, first it will extract the matching record. So this top K is nothing but the matching records. Matching to what? Matching to the user query. And whenever we are passing these matching responses, that is our custom data, along with the prompt to the LLM, it generates our custom response or custom output. And that is where, that's how we can leverage the capability of large language model to answer on our custom database. So this is the traditional RAG approach, meaning first query goes to the vector database and then we passes it to the large language model. This is the context that we pass. So this process of retrieving the top K record is nothing but retrieval, adding it into the generative, adding it along with the prompt to and feeding it to the large language model is nothing but the augmentation, and generating the final response is nothing but the generation. So that's how the RAG is defined. Now, if you go one step ahead, let's understand the basics of agentic RAG now. Let's understand what are the limitations of RAG first before jumping to the agentic RAG. For this particular RAG, the complete result that is this LLM is going to generate is based on whatever information that we are going to extract with the help of this top K results. Now, if, for example, user is asking question, let's say, user question is, let's say, basically, what is the treatment for heart attack? Let's say this is the simple question that user have asked. And in this vector store, let's say the context that you have stored, let's say you have stored the data in this way, let's say cardiac arrest. And then you have given your treatment. Now what will happen is that whenever this matching is happening, whenever you are extracting top K records, in the user question there is heart attack word available. But in the repository you have cardiac arrest as the word. In this case what happens is this similarity matching should happen correctly in order to extract this record, or else this particular RAG operation will, if it is not able to extract this particular information, this large language model will start hallucinating, or it will start generating incorrect response. And in order to fix that, what we need to do is we need to provide a good semantic similarity algorithm so that it can identify the relation between heart attack and cardiac arrest. Now, in RAG operations, if you have large amount of data, then this RAG operation fails to extract such details, which leads to the wrong output generation by the large language model, because you are completely dependent on the query response that it is extracting, or whatever retrieval that is happening based on the user query. Now, if user is not asking the question in correct format, your model will start failing. And that's where, in order to solve that problem, the community came up with a very good framework called Agentic RAG. Let's understand the Agentic RAG very quickly. Let's take a simple example. Let's take the example from medical field itself. For example, let's say you have a use case where user is asking question related to the medical field, and then we have a AI system that is talking to different databases and extracting the details and giving it to the user. Now in this case, let's say we have three different sources of information. Let's say first source is, let's say, patient information. The second source we have is, let's say, emergency services. And the third one that we have is, let's say, is the disease information. Now in this case, we have these three different sources. Now this one is, let's say, the information is in PDF. The emergency contact information is there in, let's say, SQL. And this particular disease information is again there in the form of, let's say, vector store. Meaning we have embedded the information and stored it into the vector store. Now, whenever there is this LLM, which is going to, whenever there is a user which is going to ask a question to this particular LLM, what will happen? This LLM dynamically should decide which database to call. Now, if let's say user query is, give me the patient details, let's say the patient name is Ram, and please extract the details. I want to know what is the patient history, right? Medical history. So in this case, here you should have an agentic layer, or this LLM in this case is, let's say, agentic framework. It will redirect the query to this particular patient first, patient database, and from there it will extract the detail and pass to the LLM, and then LLM will generate the response and give it back to the user. If the user question is, let's say, okay, at particular XYZ address, let's say there is some incident happened, some accident happened. In that cases, for that particular query, it should go ahead and call the emergency services. And from there, it will pick the nearest address wherever that accident happened. From here, the LLM will pick the nearest address and it will contact that particular emergency service. And it will give the response back to the user that, okay, we have contacted the emergency service. You shall expect that particular service to be there in, let's say, 10 minutes. If the user question is, let's say, the general question that, okay, the user is facing a chest pain and user wants to know that what could be the reason. So in these cases, the LLM should route the conversation, or LLM should extract the detail from disease vector store And in this case, the disease vector store will give the information which is matching to the chest pain, and then accordingly LLM will generate the response and give it back to the user. So you can see the use case here. In this case, if the user question is the related to the chest pain, and if we are calling emergency service, which may not be correct in this case, because user is looking forward for the information. User don't want to call the emergency service. If you put all these details into single vector store, there will be a problem and you will face a issues that your responses will not be correct because everything will be mixed up. In order to keep these things separate, you can have a separate databases. And this way you have feasibility where you are capturing the PDF data, you are capturing SQL data, you are capturing vector store, right? Or for emergency services, you may be calling, or for disease related information, you may be calling any APIs. So from APIs, you may be extracting or you may be calling to some another website, and from there you are grabbing the information in order with respect to that particular disease. So in this case, smart decision should be taken by LLM, and that is the task of agentic AI. And there are different types of agentic AI agentic RAG, and there are different types of agentic RAG that we will be looking into in this particular video. So I hope the overall high level idea is clear to you. So in this video, let's start with the basics of this particular RAG. Let's see how exactly this semantic similarity works. And before that, we will also understand how exactly the sparse vector similarity is different than the dense vector similarity. That also will be understanding. So let's jump into that. Let's understand the RAG framework with the help of this simple research paper. So this is the research paper which was published somewhere around in Feb, and which was by the author Aditi Singh and her colleagues. So I found this paper very interesting. It has covered all the basics of RAG. I would highly recommend go ahead and check out this paper. The link is available in the description below. Please go ahead and check out that. So as we all know that the RAG has an emerging solutions which is helping the large language model to add a real-time contextual data for our large language model so that they can respond accurately. So for the RAG, there are two ways. First one is the Naïve RAG and second one is the advanced RAG. But before that, as we discussed earlier, the disadvantages and how exactly the agentic RAG is different from the RAG or traditional RAG, let's understand this with the help of this particular diagram. So we have already seen these different limitations of the RAG and the challenges, or the hallucination, inaccuracies, the limited contextual integrations, and it is a static workflow and it lacks the adaptability, meaning we cannot add lot more modularity into the agentic AI application or a lot more modularity into the RAG operation. And then these are the advantages that the agentic RAG offers. Obviously, it enhances the decision making because we have multiple agents which are calling different basically the data sources or retrieve from different data sources where it has a more accurate decision making. Then we have a multi-step reasoning and iterative refinement. If the response that is retrieved or if the context that is retrieved from the databases is not correct, then agents take iterative actions. They again go back and hit to the databases and query the actual or the required information. Then it is a real-time data integration. Obviously, with the help of this, we can easily integrate the real-time data. Then adaptive learning and context awareness, because we have a multiple agents, we can easily tweak those agents to extract the appropriate data, and with this it improves the accuracy, and overall it is going to reduce the hallucination. So this is the different framework and stacks that are available which provides the where we with the help of which we can build this agentic RAG application. So LangGraph is one of the agentic framework, then we have Llama Index, then we have AutoGen, which is from Microsoft. Then we have Semantic Kernel, Crew AI, again, which is the easiest one to build the agentic AI application. Then Amazon Bedrock is there, OpenAI Swarm is there. With the help of these, we can go ahead and build the agentic RAG application. And then there are different these ways. As I mentioned, we have a Naïve RAG and the advanced RAG. So let's understand these difference between these two first. Modular and graph is very easy. Once these two are clear, then we'll be able to easily understand these modular and graph RAG. And once this is done, then from the agentic RAG side, we are going to explore the first three one, the single router, multi-agent, and the hierarchical. Because the below one, those are very simple. if you go through this particular paper, you'll be able to understand that. But let's understand how exactly the traditional RAG paradigm works. So as you already know that, okay, this is the basic components or core components of RAG, where users is asking any question, then we are retrieving the information from or context from the vector database, then we are augmenting it, meaning we are adding it into the prompt and feeding it to the large language model, and then the large language model generates the response, and that response we are passing it to the user back. So that's the core components of RAG. Now let's understand how exactly the Naïve RAG operates. So this particular Naïve RAG, let's say we have the information in, let's say, PDF, or let's say in books. That information we encode and store it into the vector store, right? Now this vector store can be a ChromaDB, it can be Pinecone, it can be Azure AI Search. This vector store can be anything. Now, whenever we are encoding and adding it into the database, so that's the basic way. Now, for the Naïve RAG, what happens is we find out the similarity between the user query and the context, whatever additional document we have added. It is totally based on the words. So we are doing the string similarity, and that's how we are calculating the or extracting the similar records from the vector store. And for that, we use this technique of TF-IDF or BM25. So TF-IDF is term frequency and inverse document frequency, which is totally depend on the count of matching words between your user query and the context that is available. So that's TF-IDF. And then BM25 is nothing but best match 25. So the name 25 is given based on the iterations that it took to popularize this particular, or to basically accept this particular algorithm. So researchers did 25 iterations. After that, that algorithm was popular, or that the community started using that. That's where it is called best match 25. And as its name suggests, best match is nothing but matching the word. Wherever you find a best match word, you extract that particular record. So that's very crude way of extracting the information with the help of Naïve RAG. And that's where it has a lot of limitations, as they have mentioned, like lack of contextual awareness, because you are doing it based on the counts. So whenever you are doing it based on counts or string similarity, you are not focusing on the semantic meaning. That's where there is a lack of contextual awareness. Then fragmented output, obviously, because you are doing the string similarity and not the semantic vector similarity. So that's where it is lagging the contextual integration. Then you have a scalability issue. Obviously, you cannot scale the key-based retrieval techniques, because those struggle with large database and often fails in identifying the most relevant information. That's where we cannot use these Naïve RAG, and that's where researchers come up with a advanced RAG. So what exactly advanced RAG is? So this advanced RAG is focus on this particular part, semantic understanding of the context, as well as on the user query, and it depends on the principle of this particular DPR, dense passage retrieval, and the neural ranking algorithm, which improved the retrieval precision. So the traditional RAG that currently we use is depend on this particular algorithm, dense passage retrieval and the neural ranking algorithm. So it is totally depend on the semantic meaning of the user query and the vector store, so that it is finding the semantically similar vectors from the vector store, and that's how it is passing or doing this retrieval operation. So let's see how exactly this dense vector search works. So you can see the dense vector search is what exactly is the dense vector search? It represents the high dimensional vector space, enabling better semantic alignment between the user query and retrieval document. Meaning it does the vector similarity with the help of dense vector. Dense vector is nothing but high dimensional vector space, and in high dimensional vector space, it is doing the vector similarity or semantic alignment, so that it is able to detect the exact, or it is able to detect the semantically similar documents that are available in the vector store. Then it has a contextual re-ranking. We have used the neural models to rank the documents. Whenever we are extracting the documents, we find the similarity score. That similarity score is calculated based on the neural models, and that's where we have used this particular DPR. Then we have a iterative retrieval, meaning the RAG introduces a multi-hop retrieval mechanism which enables reasoning across multiple documents for complex queries. If there are any complex queries, then it enables these reasoning across multiple documents, and based on that reasoning, it is retrieving the correct document out of this particular vector store. So that's how this particular advanced RAG works. So let's understand this particular advanced RAG with the help of simple example. Okay, so this we have already seen that how exactly this sparse retrieval versus dense retrieval works. This is the one that is used in DPR. Sparse meaning which is based on the TF-IDF or best match. So whenever there is user query, we tokenize it and then we extract the matching records from the vector store or from the document. Then we have ranking list. Sorry, then we have dense retrieval where user query is encoded, not tokenized only. It is encoded and based on the vector similarity, we are fetching the best match out of that. So if you see, this is how exactly this particular dense passage retrieval work. Let's say this is our user query. This user query, whenever user is asking this particular query, we are checking with respect to all the documents that are available in vector store and we are doing the similarity search. So let's say for this vector query, the top k meaning let's say we are finding top 3 passages. So this query is going ahead and doing the vector similarity, and after once the vector similarity is done, we are picking the top 3 match records where we have the higher similarity score. So that's the basic fundamental principle of this particular DPR. So again, this is one example. You can say, let's say, what is the capital of France? The spelling is not correct. Let's ignore that. So in this particular case, this is our user query. This user query we are encoding. Also, we have a encoded passage. Passage meaning a number of examples that are already encoded and stored into our vector database. Then we are finding these query embedding and the passage embedding. Based on these two embedding vector, we are finding the cosine similarity. And with the help of cosine similarity, we are extracting the top match record for this particular query that user is asking. And this is how exactly the DPR work. But let's understand this with the help of a simple example. So we'll just code this and we'll see how exactly these DPR work. So for that, we'll be requiring this particular sentence transformer and phase CPU. So from sentence transformer, we'll be importing this DPR algorithm. So let me show you quickly. So you can see from sentence transformer, we have imported the sentence transformer. Phase is Facebook AI similarity search algorithm, which help us in order to perform the similarity search. This sentence transformer is going to help us to encode the data that we have, passage as well as user query, and store that into the vector store. And then with the help of phase, we'll be able to, with the help of phase, it will store these embeddings and also it will perform a similarity search. So this is the model that we'll be using, Facebook DPR question encoder single NQ base, the model that we have loaded it from the sentence transformer. Let's go ahead and load this particular model. So this model importing will take some time because it is going to load the model. So I have already loaded the model, so it's available in the memory. So for you, it may take close to 4-5 minutes to load this particular model. Then we have a knowledge base. So in this case, we have prepared a simple example. Let's say we have these 3 queries. Let's say the capital of France is Paris, the heart pumps blood through the body, and the third example, which is very simple example that we have given, and we are calling it as a passage. So passage is nothing but the basically the documents, the different documents that we are going to ingest into our vector store. So this is the passage. Now, next one we have is the embedding. So with the help of this particular model, so this model that we have defined will be encoding the passage, convert NP equals to true. We are generating the NumP vectors, and normalize embedding. We are normalizing the embedding. So let's do that. Passage is not defined. Sorry. Let's go ahead and execute that. And then you can see this is the passage embedding shape that it has generated. Now this is the standard shape that it is picking, 768, which is the shape defined by this particular embedding model. So 768 is nothing but the length of vector, and 3 is nothing but the rows. Because we have these 3 records, for each record, it has generated 768 dimension vector. So let me show you how exactly it looks like. So let's go ahead and create the index. So with the help of phase, we have created the index. And if you see, the dimension is 768 because we have picked the shape, that is the length of embedding. So if you are confused, let me go ahead and show you how exactly the shape looks like. So first of all, what we can go ahead and do is we can go ahead and embed these particular records, and then I will show you whether the shape is 768 or not. So in this particular query, let's say we are passing this user query, what is the capital of France? This is the user query. So the first part that we have is we need to encode this, meaning whatever these 3 passages that we have encoded. Similarly, we need to encode the user question. And if you can see here, the length of user question is again 768. Let me go ahead and print the embedding. So if you see the embedding, you will see this is the vector user question vector that it has generated, and this vector length is 768. If you want, let me go ahead and show you passage embedding as well. For passage embedding, if you see, there will be three vectors. You can see first vector, second vector, third vector, and each vector is of size 768. So you can see this is the first vector, and if you take the length of this vector, it will give 768. You can see that's the length of this vector. So all the passages we have converted to 768 vector. Then also the user query we have encoded it and converted it into 768 vector. Now the vector sizes are similar. 768 by 768 will be able to do the cosine similarity or semantic similarity comparison. Now that's this particular task. So we have defined k equals to 2. Then we are calculating d and I. I is the index and d is the document. And then we are, with the help of index.search class that is available in phase, we are doing the query embedding and k. This query embedding we are passing, and we are searching top 2 records into this particular index that we have created. So if you see, this is how exactly it will return. So you can see this is the array, document array. 0.94 and 0.66 is the score of this particular document. This is the match score, and these are the array, meaning in this particular index, these particular documents are available at position 0 and 1. Let me quickly show you how exactly it looks like. So you can see for first document, the probability is 0.96, meaning the score, matching score, not probability, matching score is 0.94. So if you want to see this, we can go ahead and see. If you can see, query is, let's say, what is the capital of France? Rank 1. At first rank, you can see at 0th rank, we have the capital of France is Paris with score 0.9437. So this is the score, meaning at first index, we have this particular vector. So basically this query, which is rank 1, and rank 2, we have heart pumps blood through the body, and the score is close to 0.66. You can see 0.66 is the similarity score. So that's how this query similarity works. The advanced RAG that we have seen, how exactly the DPR algorithm works. So this is how the DPR algorithm works in order to find the find out the semantic similarity. So in this case, let's say if the user question is, let's say the user question is just the capital of France. In that case also, it will convert that vector into 768. Now you can see the vector that it has, the embedding vector that it has created will be slightly different. And then again, if you are doing this matching, now you can see the similarity score has reduced. And then if you do this particular search, again, still it will give that, okay, the capital of France is Paris, because we have asked the question capital of France, and still it is giving the correct result. That's how the semantic similarity DPR algorithm works. I hope this particular part is clear to you. I will attach this code link into the description, so please go ahead and check out that and play with couple of new examples. The first example that we saw, right, related to the medical field, cardiac arrest versus the heart attack, you can go ahead and try that particular example here. Okay, moving ahead with our algorithm, the next approach we have is the modular RAG. So first we started with the Naïve RAG, then we have seen how the advanced RAG works. Now let's go ahead and see how exactly the modular RAG works. In the modular RAG, it is the combine or hybrid approach where we have used the sparse encoder BM25, best match 25, with dense retrieval technologies such as DPR, dense passage retrieval, to maximize the accuracy across diverse query types. So that's the simple modular RAG. It's just the hybrid algorithm that the researchers have developed. Then next one is the graph RAG. Again, graph RAG, you know the basics behind graph, right? It is a node and edge structure. So with the help of node and edge structure, it gives us this visibility with the help of which we can go ahead and extract the similar records. So you can see node connectivity captures the reasons over relationship between the entities, meaning the nodes are the reasons and the two reasons that are connected, meaning let's say the context. Each node represents a context, and the edges that connects to these nodes is nothing but the relationship between these edges. So basically the similarity based on the context similarity, the graph collates all the similar nodes together and they connects it with the help of these particular relationship or edges, and on those edges they can capture the similarity search, how the edges are connected to each other. For example, let's say we have these particular graph structure. In this case, these graphs will be connected in this particular fashion, right? Let's say this word is art. Let's say this word is attack. And this word is, let's say, Germany. So as we all know that heart and attack are closest to each other, but Germany is not. So in this case, this particular node, these nodes will be very much close together. Germany will be far away. And in this case, this particular edge, which is defining the relationship between them, the similarity score might be, let's say, 0.80. In this case, the similarity score might be, let's say, 0.23, something like that, because these two are very, very different. Now, attack and Germany, they are close together because there might be let's say the context might be some attack on the country Germany. So in this case, again, here the similarity will be closer, maybe let's say 0.70, but the Germany and heart may be far away from each other. So that's how this particular RAG stores these particular different vectors or stores these particular nodes together, and that's how it helps us to retrieve the similar, semantically similar words from these particular vector stores. And again, there are a couple of vector stores that are available to store RAG kind of databases like Neo4j. So these Neo4j kind of databases help us store these kind of graph related structure. So go ahead and explore those. Now, that's all about the traditional RAG. Now let's start with the agentic RAG. So let's understand how exactly this agentic RAG operates. So the agentic RAG represents a paradigm shift by introducing autonomous agents, and these agents are capable of dynamic decision making. Now, dynamic decision making meaning what? Meaning the agents takes the dynamic decisions of calling these different vector stores based on the user query or based on the user intent that help us with the workflow optimization. And unlike these static systems, meaning the traditional static system where let's say we have one vector store and every time query goes to that vector stores in order to retrieve the information, the RAG or agentic RAG employs iterative refinement and adaptive retrieval strategies to address complex real-time and multi-domain queries. Retrieval meaning what? Oh, sorry, iterative meaning what? Let's say in these particular cases, let's say if you are dealing with multiple agents. So in this case, if first agent is going ahead and extracting or retrieving the information from vector store, and if the vector store information or the context extracted from that, if it is not up to the mark, then they go ahead analyze that particular and again they modify their query and hit to the vector store to extract the new information. That's how it is a iterative process, or they may go to the another vector store to see whether we can get the information from that vector store. So that's how it is iterative process. It is not a static process. That's where it helps us find the correct details from the or retrieve the correct details from the vector stores. Now, what are the key characteristics of the RAG? So first one is the autonomous decision making, because agents are self decision maker. They can go ahead and call the respective vector store as and when required in order to retrieve the correct information from the vector store. Then iterative refinement, as we mentioned, it incorporates the feedback loops. Based on the feedback, if the retrieval accuracy is not good, they go ahead and hit to the different vector stores in order to extract the correct detail. Workflow optimization, definitely, as it operates dynamically, that's where it enables efficiently extract these details for real-time applications as well. Then let's understand what are the challenges with respect to these agentic RAG framework. So first one we have is the coordination complexity. As there are multiple agents that are collaborating with each other, there is always this basically challenge while managing these agent conversation, because if you are not managing the conversation sophistically, you may lead to incorrect responses, or your agents may go into infinite loop if you are not getting the right response. So in these cases, you need to make sure that you keep refining prompt of your agent. Your agent should have a specific instructions or rules set so that they can perform based on their task. Then computational overhead. Obviously, if you are having a multi-agent framework, then Running a multiple agent obviously increases the computational power. So you need to be aware about these things, that if you are going ahead and building a multiple agent, then obviously your computational overhead is high. Obviously your cost will also high because you have multiple large language model which are handling these multiple agents. Then third one is the scalability limitations. While it is scalable, though this process is scalable, agentic AI framework, but the dynamic nature of this system can strain computational resources for high query volume. If your query volume is very high, in those cases, the dynamic nature, right, because it will jump from one agent to another agent and which will consume a lot of your tokens. Because whatever information you are extracting from your vector databases, first it will go to the large language model. So for that large language model, user query will have particular number of tokens, plus the context that is retrieved from the database will have again few number of tokens. And if these many tokens are if the conversation is happening across multiple agents, definitely there will be large volume of tokens utilized by the large language model, which will give you very high cost. And that's where the RAG framework, Agentic RAG framework, is widely used in the customer support, financial analysis, and adaptive learning platforms, where the dynamic adaptability and contextual precisions are paramount. So in this paper, they have given very good comparison between the Naïve RAG, Advanced RAG, Modular, Graph, and Agentic RAG. Now let's understand the RAG operation, single versus multi-agent. So first of all, let's go ahead and see the single agent one. So in the agentic RAG framework, as I mentioned earlier, there are multiple types. Just like we saw in traditional RAG, we saw the Naïve RAG, then advanced RAG, modular, graph. Similarly, in agentic RAG, first one we have is the single agent RAG. Now, these RAGs framework evolved based on the use cases. So let's understand a couple of them. First one is the single agent agentic RAG. This particular agentic RAG, meaning in the RAG framework, we will be having a single agent, and that single agent is responsible to navigate to different vector stores that we have. Now, the vector stores can be your PDF, it can be your SQL queries, it can be a SQL database, it can be your vector store. So the single agent will divert to these multiple vector stores and extract the details. So as you can see, it serves as a centralized decision-making system where a single agent manages the retrieval, routing, and integration information. And this architecture simplifies the system by consolidating these tasks into one unified agent, making it particularly effective for setups with limited number of tools or data sources. Meaning your single agent not only does the retrieval task, but it also helps us augment that information with the prompt and feed it to the large language model. So that's the task of single agent. So in the workflow, first of all, the query submissive and evaluation, meaning the process begins with the user query. That query, based on that query, the agent takes the decision, it evaluates the query, and accordingly it is search for the knowledge source selection, meaning it checks which knowledge source to call. For example, let's say your user is asking any question. That question first goes to your, let's say, this particular agentic system that you have built. Now, this agentic system, let's say it has access to these three different data sources. First one, you have PDF, or let's say you have books. Second one, you have, let's say, SQL database, where you need to write SQL queries, right? Without SQL queries, you will not be able to query that database. And third one, you have, let's say, API. API in the sense, let's say, the internet information, maybe, let's say, news, right? Or some market analysis, that kind of information. So in this case, your single agent is managing these conversations. It is calling based on this particular user query. It is doing this particular knowledge search, whether to call knowledge search 1, 2, or 3. Because retrieval is not only with respect to vector store. Let's say this information is stored in vector store. This is available in relational databases. This is there in open market or in open internet. So this agent is standalone agent is taking this decision to select. And again, as I mentioned, like it can be a structured database, it can be semantic search, can be web search, or it can be a recommendation system, meaning a personal recommendations based on the contextual queries, like user information or any other information that is based on some recommendations. And then we have a data integration with LLM. That data we are passing it into the LLM, and then we are generating the output. So you can see the simple diagram where you have, let's say, user input. That user input is a query. Along with that, we add a prompt. That prompt we pass to the single. So this is our single retrieval agent, retrieval router agent. That's where the name is given, retrieval router agent. Then this agent decides which tool to call, whether to call first vector store, second vector store, or web search. Now this first vector store, it may be, let's say, PDF. The second vector store, it may be, let's say, some books. The web search may be, let's say, the news articles, right? So based on that, it will decide the single agent and extract the information. So that's how the single agentic RAG works. Let's understand the key advantages of this. As it is a centralized and simplicity, meaning single agent is responsible to handle all the conversations and retrieve the information. That's where it is simple. Second one is efficiency and resource optimization. As we are using single agent, there is not going to be much resource utilization. There will be limited tokens. There will not be multiple to and fro conversation happening between multiple agents. So this is, as compared to the multi-agent, it is optimized from the cost perspective. Third one is the dynamic routing. Obviously, as it is a agent and it has a large language capability, it is dynamic in nature. You can add a new databases as well as and when required. Fourth one is the versatility across tools. It supports, as it is an agent, it supports tools and it can do the customization task as well. It can hit to in external APIs, external data sources, and extract the information. And fifth one is the ideally for simpler systems. If you want to build any simple system where there is not lot much complexity between your databases, you can go ahead with the single agent RAG. And the researchers have given very good example where they have given this particular example of, can you tell me the delivery status of my order? So let's understand how exactly this is going to work. So the first process is query submission and evaluation. Whenever user is asking this question, can you tell me the delivery status of my order? That particular query, first it will be received by the coordinating agent. As in our case, we have single agent. That single agent is then determine the most appropriate source of information, right? And then first of all, it will go ahead and check what are the different knowledge base that I have. Then based on those knowledge base, it will go ahead and select the knowledge base. So in this case, let's say retrieve tracking details from the order management database. First, it will decide, okay, can you tell me the delivery status of my order? Let's say I have ordered a mobile phone on Flipkart, let's say. So first, what exactly it will go ahead and do, it will extract the tracking details based on the order management database. Now this is our SQL database, right? All the order related information, when was the order placed, who is the customer, right? Where exactly is the order currently, all that information, it will extract it from the SQL. So for this, the agent will call the SQL database. Second, it will fetch the real-time updates from the shipping provider's API. Let's say this mobile, let's say any particular company is selling, let's say Samsung is selling this particular mobile. So it will go ahead and check on Samsung whether that particular item is available or ready to pick or not, right? Accordingly, it will take that decision. So for this, it will go ahead and call the API, external API. Third one, optionally, it will conduct a web search to identify local conditions that is going to affect delivery. So it may call, let's say, the Google API in order to extract the traffic information. It may call, let's say, the weather APIs in order to extract the weather conditions, and it will, based on that, it will take the logistical details information. Now these three information, then it will be passed to the single agent, right? And then this particular agent is then going to, based on the prompt and the user question, generate the response. So now you can see how exactly beautifully it will generate the response for that. So that's how it will happen. You can see then it will integrate with LLM and generate the final response. So they have given simple example like your package is currently in transit and expect to arrive by tomorrow evening, something like that. That's the simple single agent RAG system. Let's understand what exactly is the multi-agent agentic RAG system. So similar to the single agent, now the only difference is that here you will have multiple agents and each agent will be responsible to handle or tackle the respective databases. So you can see instead of relying on single agent to manage all the tasks, reasoning, retrieval and response generation, the system distributes responsibilities across multiple agents, each optimized for specific role of data source, meaning each agent will have its specific role and data sources. And in the workflow, first one is query submission. It will take the query from user. Second, it will specialize retrieval agent. It will identify which agents to call for what task. So it will decide that. So you can see for first agent, it will handle the structured response, let's say SQL based databases. So in our first query, if you take this particular same example, first it will retrieve the tracking details from the management database. So it will hit to the SQL database, like let's say PostgreSQL or any other, let's say MySQL database, and it will extract the order detail. Now order detail can be, let's say, what is the product, who is the customer, all those information it will extract. Agent 2 maybe, let's say, is for a unstructured information, let's say PDFs or books. So in this case, it manages the semantic searches for retrieving unstructured data from sources like PDFs, books, or internal records. So in this case, let's say PDF is nothing but a bill, right? Bill invoice that is placed for that particular order. So based on that, it will extract, let's say, customer information or whatever information that it is required. Third agent is, let's say, focuses on retrieving real-time public information from web searches or API. For checking whether the delivery is going to affect or not, it will go ahead and call the Google API. It will go ahead and call the, let's say, weather forecast API. So that is going to handle by the agent 3. As you can see, the difference is here in the first, single agent was doing all the task. But here, for each task, we have individual agent. So in this case, accuracy will be high because your single agent is responsible to perform a specific task, right? So that you can add more instructions to single agent, and also your single agent will you can execute these agents parallelly as and when required in order to extract that particular information. But this parallel execution is not possible here because you have single agent. So single agent can go ahead and call first, then second, and then third, right? But here you can call these three agents together, and those three agents, if you are calling together, it will generate the response quickly and give it to the large language model. And let's say one more they have given is, let's say, specializes the recommendation system, let's say delivering context aware suggestions based on user behavior or profile based on the user past history. It will identify some recommendations, and that information then will be extracted with the help of, let's say, tools and access data retrieval. Meaning, for extracting the SQL database, it may use a text to SQL. For extracting the unstructured data, it may be using vector search. For extracting the weather forecast information and traffic information, it will use it will use APIs and web search in order to get those information. That's how the retrieval process will work, and then it will feed that information to the large language model, and then it will generate the final response. So you can see this is the simple example. Whenever there is user query, it will go to the prompt. Then we have a retrieval router agent, which you can call it as manager agent as well, which is going to decide which fellow agents to call. So first it will distinguish the task into three that it wants to call, let's say SQL database. Then it also needs to call, let's say, vector store, and also needs to call some API, Google API, right? So in this case, first manager will say that, okay, hey, first agent, go ahead and call the, let's say, SQL. So in this case, it may be, let's say, SQL information, or it may be, let's say, PDF information. It will go ahead and call that retrieval agent X. Retrieval agent Y will go ahead and do the web search. It will find out the weather information. Then retrieval agent third will go ahead and, let's say, extract the information from email, or it may extract the information from chat, basically the previous conversation, right? That's how it will extract the information. So that's how your manager agent will divert these or route these communications to these different agents, and then they will extract the individual information. So what are the features with it? First, it will be modularized because you have multiple agents. You can additionally go ahead and add multiple agents as and when required. Scalability, parallel processing possible so that you can improve your performance. Task specialization, each agent is specifically built to perform specific task. Your accuracy will be high. Efficiency, obviously, as the multi processing is enabled, you can see wide change in the, or you can see wide improvement in the efficiency. Versatility, because it is suitable for applications spanning across, let's say, including research, analytics, decision making, and customer support related areas. And what are the challenges with multi-agent agentic RAG? First one, it coordination complexity. because you have multiple agents, coordination becomes an issue. Your agent should delegate the task accordingly. If that delegation is not proper, you will not get good results. Computational overhead, obviously, as you will be using multiple agents, there will be a lot of computation required, and also there will be a lot of token usage. Data integration, whenever all the agents are generating the response, how exactly are you going to integrate that data? So that task of manager agent or a router agent is difficult, right? In order to consume that information and feed it to the large language model. So that's how the multi-agent RAG system works. And then the last we have is the hierarchical agent system. Now, hierarchical agent system meaning you have the agent hierarchy defined, just like manager and the fellow agents that we have seen here. First query goes to the master agent. Master agent can be your manager agent, it can be your router agent, which is going to generate the response. And this master agent knows which fellow agents to call. So let's say here you have sub-agent X, sub-agent Y, and sub-agent Z, which is going to extract these informations quickly. Now, whenever there is a user query, these master agent will decide which sub-agents to call, and then these sub-agents will call its respective vector stores, right? Or databases as and when required, or whatever is whatever access that is given to them. So again, the workflow is same. First, it will be query, then it will do a strategic decision based on the top tier agent evaluations. It will identify which sub agents to call. Then it will delegate and subordinate. It will call the subordinate agents. It will aggregate that, and then it will generate the response. And if we take a look at the example advantages, the strategic prioritization based on the top tier agents can prioritize the data sources task based on the query and complexity, which is more reliable. Then scalability, obviously, because you have distributed kind of system, so it will be scalable. Then you have enhanced decision making because you have a hierarchy defined, that based on that hierarchy the task delegation is smooth, and that's how you can see the improved accuracy overall. Challenges is obviously coordination complexity, just like multi-agent, and the resource allocation. It will be highly computational required, because high computation is required because again you are running a multiple agents. So yeah, that's how these are the three different agentic RAG systems. There are a couple of more, and for those I would recommend go ahead with this particular research paper. You can see you have corrective RAG and all other that are available or mentioned in this particular agent. But if I switch to our first diagram, so you can see here we have seen these RAG paradigm, all the RAG paradigm, and also we have seen these three major multi-agent or three agentic RAG framework that we have seen. So if you are interested, go ahead and check out these below one that are available in this particular paper. So I really like this particular paper. A huge shout out to these particular researchers, the Aditi Singh and their her colleague. So yeah, with this, I hope you really like this particular video, and this was interesting for you and this was helpful for you. So if you are interested in more such videos, please go ahead and like the video, subscribe to my YouTube channel and share it with your friends. If you have any doubts or concerns, please go ahead and drop them into the comment section below, and you will find the code link in the description below. Also, I have actually built the agentic AI framework. So if you are interested that, go ahead and check out my other videos in the playlist. The links are available in the description below. So in the next video, we'll go ahead and build the agentic RAG project, how exactly we can leverage these theoretical concepts that we have seen. If you are interested in building the agentic RAG framework, so I'll come up with the end-to-end project, and stay tuned for that particular project. Thank you so much, and I'll see you soon in the next interesting video. Thank you.